Okay. Good morning, all, and thank you for joining us. My name is Veronica Wild, and I'm here on behalf of Carbon Solutions. Before we begin, a quick note that today's webinar is being recorded. We'll post both a video and the presentation slides on our website following the event. At Carbon Solutions, we host webinars like this each month, and we're always open to collaborating on future projects. So if you have any ideas or you'd like to present, please don't hesitate to reach out to our team. I'm excited to welcome today's speakers, Dr. Yuancheng Lin from Tsinghua University and Carl Talsma from Carbon Solutions. Together, they'll be presenting a preliminary assessment of CO2 capture, transport, and storage opportunities for China's steel sector. Their research uses SIMCCS, or geospatial optimization software, to conduct nationwide source sink matching and infrastructure cost analyses. And the presentation will also explore regional disparities in storage potential and infrastructure cost, highlighting how GIS can inform large-scale CCS planning. With that, I will go ahead and turn it over to our presenters. Carl, if you'd like to kick it off for us.
Yeah, sounds great. I am Carl Talsma. I'm a research scientist here at Carbon Solutions. And overall, for the presentation, we're gonna talk about some work that we've done in China. I'm gonna run through kind of Carbon Solutions software pieces that we used for this project, and then I'm gonna hand it over to Yuancheng, and he's gonna talk about the specific work that he did for the project. And this kind of happened in a collaboration with Yuancheng, who was working with Eric Larson's lab out of Princeton and then out of Tsinghua University as well. And really, we've been getting kind of more and more international work with SIMCCS. We're kind of applying it to other countries, other regions, and really, we just wanted to highlight kind of work that we've done internationally, and it seems like that work has kind of expanded in the past year or so. So we can go to the next slide, Veronica. Okay, so SIMCCS is kind of our flagship software at Carbon Solutions. This is kind of what the company was built on. And basically, it's a decision support tool for building carbon capture and sequestration infrastructure. And so we've done a lot of broad regional studies where, we're deciding what's the optimal way to get CO2 from sources to sinks. How do we route the pipelines? How do we do all that? And that's, we kind of have leveraged this tool into a consulting and research tool that we use to plan CCS infrastructure projects. You can go to the next slide, Veronica. So SIMCCS is kind of based on these three pillars of capture, storage, and transport. So normally for projects that we do in the US, we use our software's Concord for the capture piece of that and Scott for the storage piece of that. For this project, Yuancheng provided much of that data for China. So we're mostly focusing on the transport, which we used CostMap for, and then the SIMCCS component, which is kind of tying all of those pieces together, capture, transport, and storage. So I'm going to talk more in depth about the SIMCCS piece of it and the CostMap piece of it here. You can go to the next slide. And sorry about we know that PowerPoint is not presenting quite correctly. We were having kind of some trouble figuring out in Teams this morning. It was giving us a little finicky trouble, but okay, so this is what SIMCCS typically looks like. You can see this is a project that we did in the southeast US, where you can see the sinks are in blue there and the sources are in red, and it's kind of routing through pipelines the optimal way to go from the sources in red to the sinks in blue over time. This is using the time model, so you can see the build out over time. And again, there's those three pieces, capture, transport, and storage, that are important here. And really optimizing the network in which you get CO2 from the source to the sink. And yeah, just kind of a visual example here. You can go to the next slide. So CostMap is our software that handles transport, and the way that it does that is through a least cost surface. So basically, what CostMap does is it collects geospatial data. We apply a weight to that data, saying whether the pipeline is going to be more costly or less costly, and then we run a shortest path algorithm to determine what the optimal path between 2 points is. Um, so yeah, this is what our typical cost surface would look like for the US. That's yeah, this is good. So you can see the software is collecting all these different types of geospatial data, like topography, like crossings, which would be roadways, rivers, railways. And then there's things like land use, land cover data, existing pipelines, population density. These are all things that typically go into our CostMap Pro software. And then we apply a weight to that. We apply both a routing weight and a cost weight to create two separate surfaces, the cost surface and the routing surface. The cost surface is going to represent how much a pipeline actually costs for that region. So that's very specific, like dollar amount. Like, is this land feature increasing the cost to build a pipeline or decreasing the cost? And then the routing surface is going to be a little more um, qualitative. It's going to include things that might not affect the cost of the pipeline, but would determine whether we want to build there or not. So that's going to include things like environmentally protected land. It's going to include things like population density. Maybe we want to build further away from people. Yeah, I would say, national parks, regional parks, things like that are like classic things where it doesn't technically you could build a pipeline there, it wouldn't cost anymore, but because those places are protected, we don't want to route our pipeline through a national park. So we end up with these two separate surfaces. One is the cost surface and one is the routing surface. And we can we run this at varying spatial resolutions. The highest we do is 720 meters, and that's for big national level runs. And for the China project, I think we did 720 meters. But we have run it as low as 30-meter resolutions if we're just doing a CCS project like within a single city. It can get pretty fine grained, and it's designed to be customizable and flexible. So you can input really any kind of geospatial data into this and apply your own weights and see how it affects the routing. One thing for this project specifically is we kind of had to start from scratch, and Yuancheng provided a lot of the input data for this that he collected for China. So we had a lot of good data going in. We had to kind of adapt the software to be able to run in China. And a lot of that had to do with projections and allowing the software to be more flexible in terms of spatial projections for the data, which we were able to do. But really, I think this was one of our first projects that we did internationally. It kind of opened us up to finding more global sources of data that we could apply to any region. And that has been really useful for some of these other projects. We can go to the next slide. I think I had some more. Okay, so once we have the cost surface, what we do is we apply Dijkstra's algorithm. So you can imagine we have a network of nodes. We have a source node, sink node, several source nodes, or several sink nodes. And then using the cost surface, we apply Dijkstra's algorithm, which is just shortest path algorithm, which will find us the optimal route, which minimizes the routing weights that we came up with in the previous step. So we're going from point to point. The algorithm is finding the minimum routing weight, the total routing weight between those 2 points, and that ends up being our pipeline route. Then what we do is we use the cost surface to apply the cost of that pipeline once we have the route. So you can go to the next slide. I think I've got one more. Yeah, okay. So this is what a typical SIMCCS result would look like for the US. You can see, again, we have sources and sinks and all the pipelines going in between. And this is just an example of a big national level run that we would do. But yeah, there's challenges in applying the software to China specifically, mostly have to do with all the data collection. There's a lot of data, especially that goes into cost map. There's all the geospatial data that we need to be able to develop kind of quality routing and cost estimates for the pipelines. But we know there's a lot of opportunity for CCS projects outside the US, depending on a lot of things. You know, other countries have different emissions profiles. They might be a lot more carbon intensive than the US is. And CCS could be a lot more viable in other countries, depending on those emission profiles, depending on the regulatory state, a lot of things. There's a lot of opportunity for CCS in other countries. So we've kind of started to, out of this project, we've started to look for more global sources of data that we can feed into cost map. Specifically, how do we come up with a global cost surface to start with, where we can figure out, you know, pipeline routing and pipeline cost. And then maybe once we have that global source, we can bring in more regionally specific data, more nationally specific data, and add that to that global surface and make it more suitable for different countries. And yeah, the work that Yuancheng is about to talk about was kind of our first foray into international work. And since then, we've had several projects in South America and Asia that have kind of followed this work. So I think this is my last slide, Veronica, and I will hand it over to Yuancheng, and he's going to talk more specifically about the work he's done in China.
Okay. Okay, thank you, Kara. Thank you for your introduction for the SIMCCS. And next part, I will give a brief introduction about our China steel sector. That is the assessment of CCUS, the CO2 capture, transport, and storage network of CCUS for China's steel sector. And we use SIMCCS in this project to access this network. Okay, let's continue. Okay, next slide. Next slide. Okay. Go back. Okay, this one. Okay. You know, for China's steel sector, China's steel sector is the top one industry emitter in China. So the decarbonization of China's steel sector is very important. But you know, it is a typical hard-based sector. So CCS and other technologies like hydrogen is very important for decarbonizing China's steel sector. So here we want to assess the CCS, the cost and the potential of CCS in China's steel sector. So here we want to conduct a deep analysis of CCS network in China's steel sector. And this is the background. Okay, next slide. And you know, we want to assess the CCS network in China's steel sector. We need to conduct a very detailed sourcing match analysis. Sourcing match analysis, which means that we want to estimate the CO2 sources and the CO2 sinks, and then we need to assess the CO2 transport network, and this is why we use SIMCCS to quantify, to access the whole CO2 capture, CO2 transport, and CO2 storage network. So for this project, first one, we need to answer 3 questions. The first one is how much CO2 can be captured at which sources, and the second one is where to store CO2 and how much CO2 can be stored, and the last one, that is how to construct CO2 transport infrastructure and how much is the cost. And this is the advantage of SIMCCS. Okay, next slide. Okay, we also conduct a brief literature review of previous studies that we found that few studies can be found on China's steel sector, and most studies just focus on the coal-fired power plants, and maybe few studies can be found on the steel sector. So this also emphasizes the importance of this study. Okay, next slide. Okay, the aim of this study is a detailed sourcing matching analysis of China's steel sector, and we aim to answer the following 3 questions. That is, how much CO2 can be captured, and where to store CO2, and the last one, that is how to transport CO2 from sources to storage sites, and how much is the total cost. Okay, next slide. Okay, as we mentioned, we have three things to do and 3 questions to be answered. And the first one is the estimation of CO2 sources in China's steel plants. That we want to, if we want to conduct a detailed sourcing matching analysis, the first one we want to know where is this CO2 sources. So here we collect data from some datasets, and we collect 227 plant level CO2 sources, which means that we estimate 227 steel plants, and we estimate the CO2 emission of each plant, and we estimate the captured cost of each plant, and most important, we estimate the location, which includes the longitude and the latitude location of each plant. And finally, we provide 227 plant level CO2 sources and used for the data input of SIMCCS. Okay, this is about the estimation of CO2 sources. Okay, last slide. Okay, let's turn to the second work, that is the estimation of CO2 storage capacity in China. Here, we based on some previous studies, we select 12 deep saline aquifer to use for the geological CO2 storage, and we estimate the CO2 storage capacity in these 12 deep saline aquifers, and we use some estimation method and some estimation model in studies, and to estimate the CO2 storage capacity of these 12 deep saline aquifers. So in this work, in the second part of this work, we estimate the CO2 storage capacity. And the next one, okay, next slide. And after the first part and the second part, that we estimate the CO2 sources and the CO2 sinks, we try to map the CO2 sources and CO2 sinks for China's steel sector in the whole maps, and then we can find that most of CO2 sources are located in the east of China, which that is also the most developed economy in China, which means that this area has high GDP, and also it has high CO2 emissions of steel plants. But you can find that for CO2 storage, most of these storage sites are located in the west of China. So if you just look at this picture, you can find that maybe you should spend more money to transport CO2 sources to CO2 sinks. Okay, this is just just a simple answer. So we need more 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 quantitative studies. Okay, so next part, we want to conduct a detailed assessment for the CO2 transport network. Here, as mentioned by Kara, we need to provide more inputs dataset, more GIS maps for the data inputs of SIMCCS. So here we use 8 GIS maps to construct the cost surface, which means that we want to see for the whole, for example, for the for the land surface of China, which part is expensive for transport CO2 and which part is cheap for transport CO2. And then we combine these maps together and then we can get the cost surface. And we use this cost surface and then we put the CO2 sources and the CO2 storage into this cost surface. And then we use these 3 parts, which means the cost surface, the CO2 sources, and the CO2 storage size. Used these 3 parts for the inputs of SIMCCS, and then we can get the whole CO2 transport network. Okay, next slide. Okay, and for to get a more completed, you mean a more comprehensive pictures of the CCS network in China, we set 3 scenarios. The first scenario is the full capture, which means that all the CO2 emissions of steel plants can be captured. We set the best capture rate is the 90%. So 90% means the full capture. You can see that in the full capture scenario, most all the CO2 can be captured and to be transported into the nearest storage sites. And for this scenario, you can find we should spend the high transport cost, which is about over 50%. It is a very high cost. Okay, next slide. But if you set the total capture target to the medium capture, which means that reduce from 90% to the 60%, you can find that the transport cost will be lower, and it will be the 44%, and which means that for some sources that is very far from the storage sites, it will not be captured first, and only for those sources that have the nearby CO2 storage sites, it can be captured and transported. So the transport cost will be reduced to 44%. Okay, next part. Next slide. Okay, you can also verify this conclusion in the low capture scenario. Low capture scenario, which means that only 30% of CO2 can be captured. Okay, in this scenario, only 44% 41% of the transport cost, which means that only some sources that has a very good storage sites nearby, it can be captured. Okay, next slide. Also, we conduct some very detailed regional source sink match analysis using SIMCCS. We can find that for this region, that we will spend a very high cost to build the CCS network, which means include the CO2 capture, CO2 transport, and the CO2 storage. And you can find the whole unit cost. I mean, the unit cost includes the CO2 capture, CO2 transport, and CO2 storage cost. And in these three regions are all over $80 for each ton of CO2. But in China, China's carbon price is just about $10 of each CO2. So I think maybe in China, if you want to build a CCS network, the cost is still very high, and maybe we should do a lot of things in the future to reduce the cost. And okay, next slide. Okay, next slide. I just want to present some brief. No, go back. Okay, this one. This one I just want to give a brief conclusion of this study. The first one is that the CCS is very expensive, and it needs a very high cost of pipeline construction cost in China. And the second one is that we can conduct some CCS demonstration projects that in some areas with very good storage situations. And the third is that maybe we can promoting the utilization of captured CO2, which means that we change CCS to CCUS. Maybe it will be a very effective way to earn more money for a company. Maybe the company would like to do something like to utilize CO2 to get more money. And the next one is that maybe as we mentioned that most of these CO2 sources are located in the western area of China, and for western China, this area are near the ocean. So maybe the offshore CO2 storage is a promising way for China's CO2 storage in the future. Okay, next one. Okay, this is just a brief introduction for this project. Thank you. Okay, Kara.
Carl, any final notes to add?
I don't think so. It looks like we have a couple questions already in the Q&A. This first one is, do you also map EOR fields as a utilization storage option? Which I don't think so, right, Yuancheng? There's no alternative utilization options in the modeling here, right?
Sorry, what? Where's the Q&A? I cannot find the Q&A.
At the top banner, there's a Q&A. It's right next to the chat. If you click on that, there's a couple questions in there.
But I cannot see the chat room.
It should be under the Q&A. I can go ahead and read it again for you. Did you also map EOR fields as a utilization and storage option?
Sorry, what? I cannot hear. Sorry, what?
The question is, did you map enhanced oil recovery fields as a utilization and storage recovery option?
Sorry, I cannot fully understand.
Right. I think the storage options were all just geologic storage without utilization. Was my understanding, I think. But we have done work with SIMCCS with other utilization options before. Maybe we'll move to the next question. So this next question is, what sources did you consider for capture power station and BFG or more? What was the overall capture rate for a facility in your models?
Okay. I can answer this question. You know, we just consider the, you know, for the SIMCCS model, we just take the whole plant as the whole parts. We do not consider the facility level like the BF boiler, like anything facility. We just take a steel plant as a whole parts. Yes.
Okay, great. I think that's all the questions we have in the chat in the Q&A right now. Here's another one coming in.
Okay,
you can see that. Okay. I'll just read it aloud. For any region, US is my interest. Have you reconciled the cost, transport, and/or storage predicted with more detailed project-specific cost estimations as projects get further developed? Feed costs, I'm wondering what level of cost accuracy and NPV accuracy the tool may provide. Minus 50% to plus 100% or tighter. We have not really been able to get our hands on a lot of feed costs. We've done some feed studies in Wyoming that are more, I would say, granular, where we're really in the weeds on how much the pipeline will actually cost and talking to engineering teams on that. But not a lot of a lot of these like large scale CCS projects are obviously like broader in scale than what is being built out. So we haven't had a lot of cost estimates to really compare against, is what I would say to that question. Then this next question, what are the capture costs based on in the China models, US capture costs, or any data from Baotou steel plant, etc.?
Okay, I try to answer this question about the capture cost. You know, it is a very our capture cost I calculate based on the CO2 emission, the CO2 emission value that we have you know, we in our Princeton teams. One of our colleagues have calculated a curve like this that is about the relationship between the capture cost and the CO2 emission amounts, and then we calculate the CO2 capture cost. And I understand that the CO2 capture cost includes the fixed cost and the flexible cost. Okay, so it's like it's calculated like this, and we calculate the capture cost based on the CO2 emission amounts and the fixed cost and the flexible cost. Yes,
yeah.
we use China dates, not the US cost.
Okay.
And
I can.
Okay, if you are interested, you can see our papers, and I can try to send the link into the chat box.
Yeah, that'd be great. And I'll talk about our so we use for the US runs in SIMCCS, we usually use Concord, which similarly pulls emission rates data from reported GHGRP or I'm blanking on the other source, but basically what the reported emissions rate for the annual emissions rate for the facility is, and we break down the facility. Is it a natural gas plant? Is it a coal plant? Or is it, other industry? Is it cement? Something like that. And then we have separate engineering models which will estimate the capture cost based on the emissions rate, how many capture trains is required, and then it breaks the natural gas down into individual streams of CO2, which is more complicated. I'm not totally in the weeds on Concord, but basically there's an engineering model for each sector and each stream within each sector that we like to use. But yeah, it sounds similar to what Yuancheng did on his end, but
Oh, I'm sorry. I cannot send the link in the chat box. I don't know why. Okay, there is a question about what sources did you use for cost of capture on an integrated steel facility? We just estimate the plant level CO2 sources, and then we select a steel plant database, and we use this database to select 227 steel plants. Just the BF steel plant, not the electric steel plant. For electric steel plants, most of CO2 are from the electricity generation. That is not the on-site CO2 generation. That is off-site. That is from the power generation. So what we consider for CO2 capture, just to consider the BF route still means, this is very detailed. It is very detailed technical details. So maybe you can understand some things about our source selection.
There's another question in the Q&A. Do you account for potential changes in future emissions resulting from shifts in steelmaking processes, such as transitioning from BOF to EAF? I don't think you're doing that here, Yuancheng, right? You are using current steel emissions and not estimating anything about the future. Is that right?
Sorry, what?
There's a question in the Q&A about did you account for potential changes in future emissions, such as transitioning from BOF to EAF?
The transmission what? Okay, this is a question. Okay, I cannot
Yeah.
see this question in the chat box. Can you repeat?
Yeah, maybe it's helpful if I just copy and paste it into the chat. Yeah, here we go. Do you account for potential changes in future emissions resulting from shifts in steelmaking processes?
No.
Yeah.
This is not considered in our study. We just use the CO2 emission in 2020. We just use the CO2 emission of this year as the CO2 sources, and we do not consider the future changes, as you mentioned, from BOF to EAF. This is a very interesting topic, which means that if you look at the CCS network from a dynamic perspective, which means that it will change from the BOF to EOF, and how will the CCS network change in the future. This is a very interesting topic. You can try to if you are interested, you can try to conduct a study to see what will happen. And I found some studies that to conduct the power sector CCS network, and they use a power, a power scenario model to see if the power sector change from the fossil fuel based source to the renewable based source, and what will the future CCS network will change. If you are interested, you can conduct similar studies for steel sector. It is a very interesting topic, I think. Okay, let me check this paper.
And then there's a comment about the cost being high. I'm guessing you're talking about the total cost. I think the transport costs here were pretty large compared to other things that we've done. I think because some of those isolated sources were far away from the sinks. So I think what ended up happening was the program built long pipelines to capture small emissions, which ended up increasing the total cost of transport in the model, but maybe that's not what you're referring to. Is that the right? Oh,
Yeah, yes, this is the paper that's
okay.
mentioned by Zhou Xingyue Zhou. Yes, it's correct. Thank you. Yeah, about the uncertainty, actually, we do not consider many certainties. We just conduct uncertainty analysis of CO2 storage capacity. We just conduct a very small uncertainty analysis. And if you are interested, you can conduct a large scale uncertainty analysis. For example, you can try to test the selection of the CO2 storage size. In this study, I select the deep saline aquifer. Maybe you can try to select more storage size, like the oil fields, a very small scale oil fields, and if you have detailed data, you can try to use this oil field to see what is the storage uncertainty in the future. And also you can try to conduct the uncertainty analysis of the some parameters in the SIMCCS, and also you can try to conduct the uncertainty analysis of the CO2 sources estimation. And if you are interested, I think there are much work to do in the future for the uncertainty analysis. And maybe Kara, do you have some idea for the uncertainty analysis in SIMCCS?
Yeah, it ends up being pretty difficult. Uncertainty in SIMCCS, we've done it. It's difficult because there's so many moving pieces.
Yes, I think maybe we have lots of parameters in SIMCCS, so maybe
right,
it's
exactly. One way that we've handled uncertainty is by adjusting parameters, kind of doing Monte Carlo, but not exactly, but basically adjusting the inputs, aggregating the output. So doing several SIMCCS runs with differing inputs, aggregating the outputs, and then kind of seeing which sources capture all the time, capture a percentage of the time, which pipeline routes we see consistently across all those scenarios, kind of which pieces of the network are deploying the most frequently, and then we would say those are more robust pieces of the network. But it takes a lot of just computation to do that, especially for this was such a large problem for SIMCCS that we had to break it up into smaller pieces. It was hard for SIMCCS to solve. It was like a very complex run of SIMCCS. For simpler runs, we can do kind of that uncertainty, but for this project particularly, it was taking a long time to reach a solution. So it hard to do with a large run that has a lot of sources, a lot of sinks. Those kind of tend to be harder for SIMCCS to solve.
Okay, both. I think I will take this pause and questions as an opportunity to go ahead and close out today's webinar. Again, thank you both for presenting and for taking time on our monthly webinar. Again, we do host these every month. This will be posted onto our company website for anybody interested in seeing the recording. As always, don't hesitate to reach out to myself or Carl with any follow-up questions. And thank you all for joining us today.
Thanks, everybody.
Okay, bye, Kara. Thank you.
Bye-bye.
Bye.